The broadcast is now starting. All attendees are in listen-only mode.
Hello, good morning, afternoon, or night, depending on where you might be around the world. On behalf of EMD International, I would like to welcome you all to today's webinar on the Performance Check module in WindPRO. Today's presenter will be Thomas Sorensen from EMD International. The presentation should take roughly 45 minutes or so, and there will be a short question session at the end, followed by a very brief survey. We ask that you please submit your questions in writing in the questions section to the bottom of your GoTo interface. You can expand the questions section by clicking on the little plus symbol that's just to the left of the word questions, and then you can type your question text there in the window that appears below it. Questions will be answered during the Q&A session at the end. Questions will not be accepted once the Q&A session has begun, so please write them during the presentation. If we do not get to your question, don't worry. We will be sending out a link to the Q&A summary as well as the recording of this webinar to all attendees within the next few days. Now, without further ado, I'll give you to Thomas Sorensen, who will be taking you on a guided tour of the Performance Check module in WindPRO. So take it away, Thomas.
Hello, I am Thomas Sorensen, and I am your presenter for this webinar. This webinar has as a topic the Performance Check module in WindPRO, a new facility we have included in the latest version of WindPRO. The Performance Check module is a module that analyzes your production data from your existing turbines. There may be a number of reasons to do that. One reason might be to look into your production in details to find technical problems with your turbine. That is not the topic of today's presentation, however. Our focus is to find out what are the turbines normalized production, the production that the turbine will produce in a standard year. There are a number of purposes to do such a calculation. One, of course, is that once the turbines are operating, you have a much better basis for figuring out what the long-term production of the wind farm will be, rather than before the turbines were erected. The second purpose may be that you are using the wind turbines as references for a AP study, and you would like the calculation to calibrate the model with the actual production of the wind turbines. Of course, it may be that you bought some turbines and you just want to follow up on if the turbines are actually producing as you hope they're producing. In this particular project, which is an actual project but anonymous for the sake of the presentation, we have 5 wind turbines. You can see them here on the map marked with blue. If we open such a turbine, you can see that the turbine is a Vestas V90 turbine, 125 meter hop height. You can also see that we used the symbol for an existing turbine as opposed to a new turbine. An existing and new turbine is, of course, the same thing, except that an existing turbine allows us a few extra features. One feature is this tab here, the production data tab. Here we can enter and store a production record of a wind turbine. We will create such a record, but we will not load it at this point. We could, however, do it using the little plus down here, or simply by copy-paste into this window. Another feature of the existing turbine is the Statistics tab. The Statistics tab allows us to enter a normalized production, the normal year production of the turbine. That is for use in an AP study where WindPRO will then compare this normalized production to a calculated production, and you can check if your calculation is able to predict the actual production of existing turbines. Entering the existing turbine production is one half of the equation. The other half is the wind regime during the period of the production and the long-term environment. For this purpose, we can either use a commercial index. In this case, we have an EVAT index. You can see here, these are the regions of the German EVAT index. And you can see that this wind farm here is located in the crux between region 16, 13 and 17. A production index is an index telling you how much a wind turbine will produce in a given month compared to the normal production. An index value of 95, for example, means that that particular month has a production value of 95% of the normalized production, of the standard month production. Whereas 120 is 120% of the standard production, of course. Let's just go back here. We also have two other options for creating a wind regime, that is by using measurements. Now, in order to create a normalized production, we need a very long period, and for that purpose, mesoscale data are highly suited. We have in this project two data points. One is the MERA data, and the closest point is located up here. You can see that the MERA data consists of a data set in 50 meters height, and we have 20 years of data from this point, all as hourly values. The other data set we have here is the EMD convex data set. The EMD convex data set has a point very close to the wind farm. It is in fact inside the wind farm. And if we look at the properties of this data point, we can see that we have a number of different heights. So I wonder if we cannot find a data point which will fit the height of our turbines, 125 meters. We have also here 20 years of data at hourly in an hourly frequency. Now, the MERA dataset is downloadable as online data in WindPRO and only requires a license for the MCP module and the Meteo module, of course, because that's how we start. The EMD convex data is a data set that requires a license for the EMD convex data, but once you have a license for the EMD convex data, you have unlimited access to EMD convex data. So you can download as many as you want and as often as you want data points. The MERA data set covers practically the entire world, whereas the EMD convex data covers Europe, and we can actually on request take it down points from other parts of the world as well. But that would we probably do for a fee. So these are our wind data for this session. The next point of the procedure is to open the performance check module. We have this icon here, performance check. If we click on it, we can start a new calculation, and I will call it monthly production. And we can now open or load our turbine production data. Now we have for this project monthly production data, and you can see we have a text file with date and production, availability, and so on for these 5 turbines. A standard ASCII text file. So we can load this text file, import, OK. Note the yellow buttons. The yellow button convention in WindPRO is that we highly suggest that you press the yellow buttons as your next choice. So we can add the file, and the file was located here in data, product monthly production. We can use auto detect so WindPRO can figure out what we're looking at. Then we need to sort out the names of the turbines. Names can be, the ID of the turbine can be given in many different ways, so there's not one unique way, but this wizard can help you to easily identify the turbines. So we have several turbines. We have one data file. And we can now point out the first turbine, the second turbine, and the last turbine. Now, the turbine name ID is obviously part of the header. So we use this checkbox, allow turbine ID to be a substring of the column, and as delimiter we use dash and press OK. And you can now see identify the turbines as called WEA30, WEA29, WEA27, and so forth. So now we can select all columns and make them power production, apply, and then we can specify those which are not power production. Obviously, date is a timestamp, date, and we can write day, month, year. And we'll see that now out here in converted we have a date. That means the date is recognized. The year, we said ignore. Then we have a lot of production data and a lot of availability data. All the availability data we will call availability, 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 and again. And you can see here, these are the figures that our data have been converted to, and that looks all quite right. Now that we have set up a filter, we can continue to pair and load. We have a yellow button here, add. Let's click it. Now we can see that in these layers we have 5 existing turbines. I'll just select them. And we can take the one called WEA26 and check the, I think we missed it. Let's just go back. Yeah, maybe we missed it here in the wizard. We have the first, the first turbine, second turbine, and the last turbine. Yeah, that looked quite right. Okay, and now we get all 5 turbines. And now we can pick them. 29 and 30. Now they have all been matched, and we can load the measured data into the turbines. And you have a little stylized map down here to identify the locations of the turbines. And on the time series tab, we can now see each turbine with the production record loaded. So now we are ready to proceed with the second half of the data, which are the wind data. And we proceed directly to this wind index WCP tab on the main graphic tab. You can see that there are already some data. On my computer I have the Danish wind index as a global data set, so it will always pop up. I'm not really particularly interested in the Danish database in this case. I want a new database, so I can edit this dataset, add a user index base, and I will call it IWET 11. I have a nice spreadsheet, the complete EWET 2011 spreadsheet. You can see there are 25 regions. So let's enter 25 regions. This reference pair is quite irrelevant and only for information when we are entering an index like this, so I just leave it open. Okay. And then I can go back to my spreadsheet and select all my data, copy, back to WindPRO, and read from clipboard. First line with data was line 1, no? Line 2 it is. So, okay, and there we are. Now we have 25 regions and a bunch of years. We can load an index region map. You can see I have this IRM map here, comes with WindPRO. Okay. Okay. Yes, that is fine. Good. I can see my site here is located in region 16, near region 13 and 17. And we have now the different regions. Region 16 is here. See, it fits not so bad with a regression line. Let's try and add the other wind data sets. So I go back into Edit Database and add from Meteor object, add new index base, and I would like to load my mirror dataset. When we are making an index based on a time series, we use the following procedure. First, we scale the wind speed of the dataset up to the expected wind speed at hop height. Now, I'm not entirely sure what my wind speed at hop height is, but I think I will guess at something like 7 meters per second. This I can always change later, but 7 might be a good option at 125 meter, I'm guessing. The idea is that we would like our index to be relevant for the right spectrum of the power curve. If we use too high value, we will skew the data compared to the actual power curve, and the same thing if we use too low value. So let's take 7 as a guideline value, and we only use months where we have the majority of the data. That means we will not create an index for a month with a minority of data. So having scaled the wind speed to the expected wind speed at hop height, which allows us to use data at 50 meter from the mirror data, for example, we will then apply a power curve to the data. And in this case, we have a power curve from the V90 turbine. Okay. And in the time series setup, we can now pick our data set. Let's just check at 100 meter. At convex data, we have 6.78. At 150, we have 7.48. So 7 meters per second does not sound like such a bad idea. Mirror data, we pick. And I'll just set our reference period to 20 years. So all data, 20 years, and we set the normalized period to be the same period, 20 years of data. And OK. And now I will add one for convex as well. Add from Meteor. I will call it EMD convex. And again, 7 meters per second. The power curve be 90. And I think I will select the 100 meter data set. Okay. And we have an index for that as well. So let's look at all the things we can do here. First of all, when we get to actually calculate the data set, we can calculate the normalized production. We can choose two methods. We can take the sum of the production data and divide with the sum of the index value for those months. That's sort of the traditional way of doing it. Another slightly more advanced model, but also one that's been used for many years now, is the linear regression model, where we simply make a regression plot through the data set. That is my own personal preference, and we will do it for this calculation. Then we can look at our data in different ways. Let's just look at this one here. This is a time series showing the wind index, the green is a graph, and the production, the blue. And it's very easy to see if things are fairly working out or not. It doesn't tell us so much of how good it's working out, but that it is fairly okay. If we looked at, this is the convex, we can see the EVET region 16. Yeah, it looks fine. 17, also quite good. And 13, also quite alright. The mirror data, yeah, it's not so bad either. Another view would be to look at the WCP, the wind corrected production, calculated on a monthly basis. Here, instead of calculating a total normalized production for the wind farm, we do it on a monthly basis. And that allows us to see if there is a trend or an offset in the data. If, for example, we have new turbines being built next to our existing wind farm, we will expect a drop in the production. You will see that our monthly value will have which is centered around a certain value and then suddenly drop to a new level, which is the new situation for the wind farm. And of course, data from before this period we would then have to discard. We would go back to data, time series, and simply select the period from before that event and disable them. It might also be we have a trend because the turbines might be degrading, but more likely because the wind index we're using maybe has a trend, which is not a particular good thing in a data set. This particular graph shows how well, how the wind corrected production is a function of the wind index. Preferably we want a flat trend here. If we have an increasing trend or decreasing trend, that means that our wind corrected production will be a function of a wind index, and we want it to be neutral to the index values. Otherwise, we'll simply get a bias with how many top value or bottom value data points we have. Then we have this graph here, and that tells us what the production of the turbines are. Here I will just go up to the table and say we want to use the calculated average for our our production or availability. And now you can see that 98.2% is the availability of the turbine. This is turbine 26. And if we then correct it with the mirror index, we get a WCP of 4,559. Then we adjust up with the availability to 100% availability, and we get 4,441, 4,641. And that's what we have in this one. This turbine. And then we have the correlation. How well does data correlate with our index? If we just continue a little further, we have our graph. And now we'll try and filter our data, because not all the data actually lies nicely to the graph. Some data might be off simply because we have high availability, inavailability. So we can make a filter and say we want to exclude all data with availability less than 90%. And you can now see that that takes away a few of the data points. Not many, because this is a quite good data set. This outlier, for example, has now been removed. We can also click on a specific point and then remove it manually if we want. We can take out data points which are, for example, less than 60% of the average WCP value, and thereby take them out, outliers, without having availability data. The value up here, the availability value we are correcting with, is the availability value of the valid data. That means it does not include months which has been disabled in the filters. So the more we filter out, the higher this value up here becomes, and the smaller value we need to correct to get to an 100% availability result. Now we can go to our correlation again, and then we can take a look at our different indexes. You can see some have higher values than others in correlation. Let's just go to region 16. Here we are. Now they found the right region. We have a much better correlation between 0.9 and 0.95. We can click on this symbol here, copy and close, and then we can open a spreadsheet and paste the result, and you can see here we have a quite good correlation. And we can then move to this graph here, all turbines, the AEP production plus the wind corrected production at 100% availability, and we can copy that out, copy, close. As a result, the AEP value here is the average production in the valid months divided by the number of months multiplied by 12 to get a year. So that's sort of an average without using an index. Here the index corrected data, the wind corrected production is then corrected with, in this case, EVIT region 11, EVIT 11 region 16. And you can see that it's quite a bit different. Now I have a little spreadsheet where I have done this exercise for both region 16, 17, the convex data and the mirror data. And in this case you see that we actually get very nice correlation values for all the different indexes. You have the average down here. Only the mirror index actually correlate very poorly, and even that is not that bad. So we actually have a number of options which correlate beautifully to the data set. Then I also copied out the wind corrected production calculated with each index. Region 16 and region 17, that's not that big difference, we would not have expected either, but the convex and mirror data are actually quite a bit different. They're much lower, even though they consist of 20 years of data. Here we can see the difference. This is the average value of the 4 results, and this is how much each index is actually, each index gave a different result. The even index gives typically something like 2 to 4% higher value than the average, whereas the mesoscale data gave somewhere between 2 and 4% below the average. And then the next discussion is, of course, which of these are more right? That is a very difficult question because correlation-wise, they're all quite good. And certainly EVET and convex have much similar results in the correlation, but highly different results in the production. One explanation can be trends, if there's a trend line difference. And for that, you can go back to the database and simply copy out your index and see if you have a trend in it. That is a very good test. But it may also simply be a question of baseline. If the baseline is different, 20 years might not be long enough for a baseline, for example, even though that is the typical age of a turbine. So, but that is a different discussion. Now we have, with 4 different sources, created 4 different results for our turbines, and we can then pick one, for example an average, and use that as our result. And this we can also enter into our turbines. We can, I'll do that in a second. Before I do that, I'll just show you a report we can make from WindPRO. We can choose print and select all the turbines. We can make a prognosis for 2015 and we can assume a loss. Now we have eliminated the availability loss, so we need to reintroduce the availability loss. We are working on sold power, so electrical losses are already included, and all other inherent losses are actually included in our data. So the only thing we need to reintroduce is availability and maybe a degradation over the years. If we assume that these turbines are very well maintained and fixed over time, we may even be able to assume a very low degradation factor, and so we can set the assumed loss to maybe 3% over 20 years. Good. And let's try and take a view of the result. We get a report now telling us that we have our wind index is EVET 11, region 16. We have used a 90% filter using 39 months of data, and our calculated production with the 98.2% availability during our valid data points, we have a wind corrected production of 4,808 megawatt hours per year. If we scale that up to 100% availability, we have 4,895 megawatt hours per year. You have the correlation value, of course, and then you have the graphs I showed you in the presentation, the regression graph, the time series graph, the WCP as a function of wind index, and the monthly wind corrected production to see if there's any trend. We have that for each of the turbines, and then we have a prognosis, introducing the assumed loss, and using the index values for each month, January, February, March, and so on, with the scatter we have in that month, and the assumed loss, and then have a P50 and a P75 and P90 production based on the variability of that month. Please note that this does not include all the other uncertainties you have in such a calculation. It's only based on the variability of the month. But it gives you this nice trumpet graph that shows how the more months you have, the closer you get to a fixed value, the final value of the wind corrected production. And it actually shows that you need, after 12 months, you have a fairly good grasp on the wind corrected production, but you need actually quite a long time before it can be quite certain that you got it right. Yes. So now I will leave the performance check calculation, and we can enter one of these turbines. And you will now see that the production data has been automatically loaded. We have the production record for each turbine now in each object, and it will be ready to be used for different purposes. We can use it in another performance check analysis, or copy it out if you want. We can also enter our WCP into this field here. See, this was turbine 27. That was this one. So we can copy this value and put it in here. And now if we do a part calculation with this turbine, we will actually be comparing our result in the part calculation with the wind corrected production of the turbine to check if our calculation was correct. In the next version of WindPRO, this value is actually automatically exported from the performance check module. That's an improvement we didn't manage to include in 2.9. Yes, then that is it. Now we have found a wind corrected production for these turbines. In fact, we have found 4. Basically also telling us that even though this is a nice and tidy procedure, it is also very sensitive to the wind data you enter into the calculation. Okay, thank you very much for listening, and I will now send you back to Nathan.
Thank you very much, Thomas. That now concludes the presentation portion of the program. We will begin the question and answer session very shortly. I'm going to give Thomas a chance to look over the questions that have been submitted. In the meantime, I would like to excuse me. I would like to point out the ways in which you can contact us for further information about the performance check module or to place an order for it. You should be seeing on your screen here. You can look at the entire performance check manual at our knowledge base website. Also, later this evening or early tomorrow morning, there will be the video for this webinar and the summary of the question and answer session at the same website. You can also contact sales to inquire about getting a license for performance check in the ways that you see there on your screen. And if you have any more technical questions about the other ways in which the performance check module can be used, then please feel free to submit them to our support staff at support@emd.dk. So I think I will now hand the microphone back over to Thomas so that he may answer some questions. And again, I'd like to remind you, please stay with us. There will be a very, very, very short survey at the end that we would greatly appreciate your help with. So Thomas, back to you.
Yes, thank you, Nathan. We have received some questions here, and I will just answer a few of them. There's a question here if this is only a tool for the operating turbines or also for planning phase. And I think I mentioned that briefly that when you know what the turbines out there in your near your wind farm plan, how they're operating, then you can use them as fixed points for calculation. If your prediction can predict what these turbines are actually producing, then you have a higher certainty that your calculation will be correct. So that has a very great value in the planning phase. For the planning phase, you should definitely be attentive to the scatter in the result. I presented you with 2 different EBIT regions and 2 different mesoscale data, and we have a difference of more than 6% between the highest and the lowest result. 6%, that is a significant part of the typical uncertainty in a calculation, and that is just due to the choice of your reference base. And that's definitely something to be aware of also when you do your planning, if you're basing it on existing turbines. Yeah, we have a question on whether the tool can be used to detect underperformance in a turbine. And what I have been showing you is simply a calculation of what can you expect in the future from this turbine based on what it has produced in the past. And of course, if this number is less than what you were expecting, then either there's something wrong with the turbine or there was something wrong with the prediction to begin with, and the chances are that it's the prediction there was something wrong with. However, you can use this tool with scatter data directly. Instead of using monthly production data, you could use, for example, 10-minute data from the scatter data and load them. Then you will want to make a time-varying calculation based on a measured time series. If it's a ground series, it's not so difficult to make 10-minute data set, but if you have only mesoscale data, you may need to look at your data on an hourly basis. The time-varying calculation will tell you how each turbine will produce with these wind data transformed to each turbine. And you can then use the performance check to combine these two, the time series of production on hourly or 10-minute basis with a production calculation in the 10-minute or hourly time resolution. Basically, you get 2 graphs that has to match, and where they do not match, there's something wrong with either the turbine or your wind data set. If your wind data set is very good, then you can use it to identify under what conditions is it that your turbine is underperforming. Is it specific directions, specific wind speed? Is it because the power curve is not reaching the nominal power, or what is it? The tools for that are quite advanced and beyond the scope of this particular presentation, but we have some quite good experiences analyzing this. But the real issue is that you have to have wind speed data of very high quality. The nacelle anemometer is often not good enough for that purpose. So that puts some restrictions on the usefulness. But if you have measurements out there from a wind farm or very good mesoscale data or similar, then you can actually make a very nice validation of the turbine performance using the performance check module. Let's see if we have some other. In terms of whether the manufacturers fulfill their availability, it's a little more tricky than that. When you make a warranty concerning availability, you have a number of clauses saying what constitutes availability loss, and when you get your in your scatter data, you will typically see which events count towards that availability. Summing up is not particularly difficult, and you don't need a tool like a performance check to sum that up. what you should be aware of there is that there are many different kinds of availability, and some major availability losses might not be covered by the warranty. In terms of using the performance check module for calculating the wind corrected production, it does of course matter what kind of availability data you put in, and the warranted availability might not be the right one. The best one is the energetic availability, the energy loss when the turbine is down, and not necessarily the warranted, but the one counting all events, except for the permissible ones, for example, in shadow stop and other curtailments, which of course you will never get back. So you have to put in the right value to get meaningful data out. But to check if the turbine provider is complying with the warranty, I think a spreadsheet will usually do the job, frankly. Yeah, there was a question about checking the power curve of a turbine, and yes, you can actually do that. As I mentioned before, if you have scatter data for the turbine and a very good wind data set for the site, then one of the prints the performance check can provide for you is actually a power curve. I can show you where it is, though this data set will not allow me to actually show it. But if you have 10-minute data, you will actually, be able to, here on graphics, to get a tab showing you the power curve of the turbine with the wind data. Just beware that this result is very dependent on the quality of your wind data. An offset in your wind data will also be an offset in your power curve presentation. Yes, I think they were the questions we'll ask in this round. Any other questions will be answered in the summary of this presentation. Back to you, Nathan.
Thank you very much, Thomas. And that is time for today's webinar on WindPRO's performance check. When the webinar ends, a close button will pop up in your go-to interface. Please press that button and the survey will open in your web browser. It is a very short survey that should not take literally more than about 30 seconds of your time, and we would greatly appreciate your feedback. You will also have the ability at the end of the survey to request a limited time trial license for testing the performance check module if you would like. I hope you've enjoyed the webinar, and please look forward to some more information from us in the next few days, including the link to the video of this presentation, as well as the question and answer summary. So again, thank you, and have a good day, evening, or night, depending on where you might be in the world. And thanks again for your time and attention.